walk you through some things. So I'm just going to put a few things up on the board and you might want to make notes of. Okay. Electrification. So electrostatics deals with the movement of charges. Okay. So examples of movement of electric charges. When you're sitting in one of those chairs, maybe in the library, in the plastic, and you are moving back and forth, and you don't realize you're moving back and forth, and then you go to walk out of the library and you hit the doorknob, and all of a sudden, zap, you get a shock, right? That's a sign of electrification. You've electrified or you've transferred an electron from you to the doorknob. Okay? Lightning, obviously. You ever take your toque and you rub it after you've had it on your head for a while and you get the sparks in the inside of it? Okay? It's electrification. Alright? So take a balloon, rub the balloon on your head, and then you can stick it to the wall and it sticks on the wall. Again, it's electrification. Okay? So electrification is the process that produces electric charges on an object. So that's one of those words that you long word. Electrification is the process that produces electric charge on an object. An electrostatic charge is an electric charge which is confined to the object and is not moving. So the next thing you want to talk about is an electrostatic charge. And we are going to spend a lot of time with electrostatic charges and talking about how they move. So an electrostatic charge is an electric charge that is confined to the object and is not moving. So you contain an electrostatic charge. The balloon may have an electrostatic charge. It's confined to that object and it's not moving. Static electricity. Static means stationary. Ever heard of static stretching before? That's stationary stretching. Okay, so you're just in one spot, and that's what static electricity is. Static electricity is stationary electricity in the form of electric charge at rest. It's produced by friction between two surfaces in close contact. So your butt on the chair. An example of producing static electricity. It's created by the friction of it. You take the balloon and you rub it in your hair. That's static electricity that you're producing on the balloon. It's produced by friction between two surfaces. We're going to talk briefly about electroscopes. So when you were reading in your book, there's a couple types of electroscopes. You need to know the different types of electroscopes. And what electroscopes do is they help us see that there's actual charges. So an electroscope, there's some different ones, but I'll talk about the vane electroscope. It has a ball on top, okay? Got your base on the bottom here, all right? And inside it is two leaves. And when you produce a charge, or induce a charge onto it, meaning you transfer negative electrons into this or you take electrons away, it creates a charge on the leaves of the electroscope. And when they move apart from each other, that means that they have the same charge on each other. Okay? So that's called a leaf electroscope, a vane leaf electroscope. Okay? So you have in your book on page 382, it tells you the two types that we're going to look at. So an electroscope is an instrument used to detect the presence of an electrostatic charge. To produce a negative charge, a hard rubber rod is rubbed with flannel or fur. Electrons move from the fur to the rubber rod, making the rod negative. It means that you have an excess of electrons and the fur is positively charged. Okay. I'll have to find this after in the video that goes along with this. To produce a positive charge. So this is all in your textbook. I'm just giving you the paraphrasing of what was in your textbook that you should have read on Friday. A glass rod is rubbed with silk Electrons flow from the glass rod to the silk. The deficiency of the electrons gives the glass rod a positive charge. The silk becomes negative since it gained electrons. Okay. So let me talk about this a little bit more. All right. Do a demonstration. This is gonna work. Should. Okay, so right now, these are what we call pith balls. Okay, and these pith balls right now are containing a charge on them. And what I want is I want the charges to be the same so that they're not coming together. Okay, so right now they're coming together, these two pith balls. How can we tell that they're coming together? Because when I set them close to each other, they're moving towards each other, obviously. What kind of charges does that mean that each of them have? Pardon me? Positive? They both have positive charges? Opposite charges. That's more what we want to talk about, right? Okay. So we don't know if it's positive or negative. So here's what I'm going to do. I'm going to produce a negative charge on both. So I'm going to take a hard rubber rod and I'm going to rub it with flannel or fur. So I got some flannel here, or fur, okay? I'm going to rub it onto this rod. By rubbing the flannel or the fur, the electrons move from the fur to the rubber rod, making the rod negative. Okay, so currently this guy is neutral right now, which means it has the same amount of positive and negative electrons. Sorry, positive and negative charges on it. Okay, electrons. This guy, the fur, is negatively charged, which means it has more electrons than it does protons in it. So we understand that? And the moment that I rub the rod now, I'm going to transfer the excess electrons from the fur to the rubber rod. And as I bring it towards the pith balls, the moment that I touch the pith balls, the electrons that are the excess electrons in the rubber rod, making it negative, will transfer to this guy. Put that there. Okay, so now these guys are both negatively charged, and now they're going to come apart away from each other. So by rubbing, and this is, you need to make a note of this because it'll be on, you'll be asked for this. By taking fur and rubbing it on a rubber rod, you are inducing a negative charge on it. You're putting an excess amount of electrons from the fur to the rubber rod. Okay? Differently? Okay, so. Okay, so Okay, did anybody just see that? Alright, so here's what's happening, okay? See how they're touching each other now? Okay, so they got opposite charges. Now, notice what's happening. As they move it closer, where's the pith ball going? It's going away from it. So what have I done? I reduced the charge, the same charge I have on here, I've reduced it onto the pith ball. Okay, so it should, in theory, have a negative charge on it. Now, to make a positive charge, a glass rod is rubbed with silk. Okay, the electrons flow from the glass rod to the silk, reducing the number of electrons so that they're less than the protons. So by rubbing this, okay, glass rod, the electrons are going out of here and into here. So now I have more protons than electrons in this glass rod, which then means what charge is on it?
Positive.
It's a positive charge on it. So this, in theory, should come closer to us, and it will automatically get right away. So, okay, so does everybody see what we just did there? We'll do this one more time, just to demonstrate. So now, so you see it's moving away from it, right? So they have the same charge, so they're both negative charges. So it's moving away from that. And then when I take this and rub it, it should, it's not coming towards it though. So what's happening here? Which ones has the positive charge? The rod does, and they both have a positive charge on it right now, right?
Yeah.
If you're into the other ball with it.
Sorry?
If you're into the other ball with it. Or that one's still.
No. There's no charge.
Oh, there we go. So they both have the same charge, eh?
Yeah.
Both have a positive charge on it. Okay, so the main thing that I need you to take from this is to induce a negative charge on something. All right? To induce a negative charge on something, I have to put an excess of electrons into that to induce the charge. To create a positive charge on something, I have to take electrons away. Positive ions, okay, positive charges don't move. Only electrons flow freely. Okay? So if you've taken chemistry, you'll understand that what happens when you take an atom and or a an atom, what's in the outer shells?
Valence electrons.
Electrons, right? They're the ones that flow. So when you join them up to make a bond, an ionic bond, the negative electrons are the ones that join up, right?
Yeah.
And they transfer. Okay? So that's what's happening in physics as well. All right, so far? Objects that have the same charge repel, unlike charges attract. Electricity and matter. Atoms are electrically neutral. That means that they have the same number of protons and the same number of electrons. Protons and neutrons are bound together by strong binding force. Electrons are attracted to positive nuclear charge. Outermost electrons, what I just talked about, loosely held and easily influenced by outside forces. Negative charge results from an excess of electrons. Positive charge results from a deficiency of electrons. Electrical charge, scalar quantity, positive charges and negative charges. So we've got all of that. So you have a vane electroscope and a leaf electroscope. We talked about that already today. And now we'll talk about conductors and insulators. What is a conductor?
Something that transfers electricity easily.
Something that easily or readily transfers electricity or electric charges, right? Okay? So it's a material through which an electric charge is readily transferred. So some examples are silver, copper, aluminum. Basically what?
Metals.
Metals. What else easily transfers electrons? Right? Water, yeah. Okay, so metals, crystal lattice consists of positively charged particles permeated by a cloud of free electrons. We just talked about this. The binding force between the positive ions and the outermost electrons are weak so that the electrons can move throughout the lattice. This gives metals high electric conductivity. So this is in 16.5. I'm just skimming here, paraphrasing the book. You should have seen all this already. So an insulator is a material through which an electric charge is not readily transferred. Give me some examples of insulators.
Glass.
Glass, for sure. What else?
Plastic.
Plastic.
Wood again?
Wood is, yeah. Wood's a different one because it isn't entirely an insulator, but it's not entirely a conductor either. Wood does have potential to transfer some electric charges, but it's not a great one to use. It won't be small, but I mean, if you look at lightning and how it strikes, it does go through wood, right? Okay, an insulator has a lack of free electrons. Rubber is the other one that is a major insulator. Everybody should know that, right? Electric line hits your vehicle, stay in it or stay away from it because the rubber tires actually stop it, like keep it from, but the moment that you touch the ground, so if you get out and your vehicle is electrified, the moment you touch the ground, it goes through you and into the ground. So you stay within that vehicle because the rubber on the tires keeps the electricity from moving, okay? What's that? 16.6. An object is said to be charged by induction when an object induces a charge onto another. The region of the object nearest the charged body will acquire a charge of the opposite sign. The region furthest away will acquire a charge of the same sign. So flip open to page to 16.6. It is approximately 385. Okay. Yeah, 385. Actually, go to 386. In the margin on 386, there is a diagram right there that shows you what happens. So you have this rubber rod, okay, coming towards this metal conductor, and what happens here is all of the positives come there to the end of it and aligns itself because why? If this is negative, what happens here? That's right. The positives are going to attract to it and the negatives are going to repel from it, right? And so that's what happens. And then if they actually touch, these negatives flow into here and induce a negative charge on it because you're going to have more negatives than you are positives. So any conducting object properly isolated in space and charged by conduction acquires a residual charge of the same sign as that of the body touching it. When an isolated conductor is given a residual charge by induction, the charge is opposite in sign to that of the object inducing it. All right, the next part on 388. This is the important part in what we're going to get into. Okay. First things first, because we didn't do the in order here. What holds the moon and the Earth in orbit together? Gravity does, right? So there's a force. You agree? Because gravity is a force. Correct? So there's a force that attracts the two large objects together, right? We're going to do the same with electrostatic charges. Two what we call point charges. Two charges. Has an electric force between them which creates an attractive force. So this negative charge wants to move towards this positive charge. And inside this area, there is a force. Okay? So we want to be able to calculate and find out how much force there is in that area. But before we do that, we're going to look at what we call a point charge. So I'm going to get to this in a second. But a point charge is just any charge in a region. So any electrostatic charge that's in a region. And around this electrostatic charge, you have an electric region around it. So this is what happens when you go to touch that doorknob and you get that shock. This is what happens. There's an electric charge around in a region close to that knob. And as you move closer to it, you don't actually have to even touch that doorknob. You just got to get in that region close enough, and that electric shock happens to you. We call this a point charge. Okay? So this is referred to as a point charge. And around this point charge, we have a region that produces electrostatic force. And the magnitude of the force is closest around the actual point charge. So the further you get away from it, the less amount of force there is. Just the same as the further you get away from the center of the Earth, the less gravitational pull there is on you. Okay? Alright, so the further that the Earth and the Moon get away from each other, the less there is a gravitational pull. Okay, does anybody have any questions about that? So this is what we call electrostatic force. Hello. Good. Yep. Okay. Yeah, I put everybody else's in, and then I'll just make sure that either I get it or nobody travels with it. Okay. Yep. Take some time. Okay. So I have an electric field that exists around this region. Okay. So exists in a region of space, and an electric charge placed in that region is subject to an electric force. Electric lines of force is a line of force so drawn that a tangent to it at any point indicates the orientation of the electric field at this point. All that says is this, is that these electric lines of force just show the direction. They're all drawn tangent, meaning these would all make right angles, but that is irrelevant to you. All it is an electric field of force. So what happens then if I bring another electric charge into this region? Well, this is what happens. If I bring a negative one close to it, they're going to attract each other and have an electric force. If I brought another positive one to it, what's going to happen to it? They're going to repel each other, right? So these diagrams right here are in your book. Here's an electric point charge, okay? Here's one where you got two positives together. Here's ones that you have a positive and a negative, so they're attracted to each other, right? And actually, I drew this one wrong. The positive actually goes in this direction, towards this.
The negative doesn't go.
The positive goes towards it, is how they want you to draw it. This one here, flip over the page. I don't know if it's on here or not, it should be. Flip this page, please. No, it's not. Okay. So this one here is an electric static charge, a negative charge, brought towards something that contains a lot of positive charges. Okay? This would be an example. This is what we're leading into. And then this guy here is a plate, two conducting plates, one of positive charges, one of negative charges. This is what a battery looks like on the inside. This is what a battery looks like. You have two conducting plates. You have a region in between the two conducting plates so that the charges can go from one plate to the other. And this is what a battery looks like if we were to take it apart. So we're going to get into that as we go here. Okay? So, these are electric fields from some different areas and regions around it. Okay. We talked about electric line of force, so the next thing we want to do is some math around this. How do I figure this out? Okay. Electric field intensity is proportional to the number of lines of force per unit area normal to the field. If intensity is high, lines are close together. If intensity is low, lines far apart. Force per unit, positive charge at that point, blah, 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 blah. Okay, here's what happens. The more lines of force you have here, the greater the electric field intensity around this. Okay? So the more lines of force, the greater the electric field intensity. We measure that electric field intensity by measuring the amount of force around this point charge, and we divide it by the magnitude of the actual charge in that region. E equals F over Q. So E represents electric field intensity. F is force it's measured in newtons. Okay. Electric field intensity, actually I didn't put the units, is newtons per coulomb. So I'll talk about that for 1 second. And Q is the quantity of the charge. And it's measured in what we call coulombs. So E equals F over Q. This is called electric field intensity. And it's measured in newtons per coulomb. Okay. Now, I have to backtrack a little bit because I don't necessarily like the order in which this goes in. So what is a coulomb? 1 coulomb of charge. 1 coulomb of charge refers to the number of electrons that are in and around that area. In this case, 1 coulomb of charge is 6.25 times 10 to the 18 electrons. So 1 coulomb of charge is 6.25 times 10 to the 18 electrons. Yeah, there's lots of them in there, right? Okay, what we have a hard time doing is understanding what electricity is. Electricity is the flow of electrons. That's what it is. It's the flow of electrons that creates what we have today is what we refer to light, whatever, anything you power up through electricity is the flow of electrons. Okay? 1 coulomb of charge represents a flow in which you have 6.25 times 10 to the 18 electrons. And then if you had 1 amp, that's 1 coulomb per second. That means that there's 6.25 times 10 to the 18 electrons flowing through that spot in 1 second. So this is all going to lead up. And as we are, this is the very basics of what we're going to do, which is study and figure out electricity, resistance, voltage, the whole bit. Okay, we're going to get to understand all of this. So what is the charge on 1 electron then? what is the charge on one electron? If there's 1 coulomb is 6.25 times 10 to the 18 electrons, then what's the charge on one electron?
3.6 times 10 to the negative 19.
So that's the charge on one electron. Okay? These are the two ratios that you're going to use. Now, this is a remarkably small number. This is a remarkably large number. So we tend to use charge as microcoulombs. So we got to go back to what we did at the start. We have to understand what microcoulomb is. So 1 microcoulomb is equivalent to 1 times 10 to the negative 6 coulombs. So instead of writing out coulombs a lot of the time, we'll write it as microcoulombs. That way the numbers aren't so small. All right. So what's the point of all of this? Well, the first thing that we want to do is we want to be able to measure the force between 2-point charges. What is the force between these charges? How much force is there being created to pull that here? Okay? How much force is there? Coulomb's law. By definition, Coulomb's law. The amount of force, just don't write this down, the amount of force between 2-point charges is directly proportional to the product of the charges, the product of the magnitude of the charges, and inversely proportional to the distance squared between them. It's proportional to the product of the charges and inversely proportional to the distance squared between them. So what does that mean to you? F equals K Q1 Q2 over D squared. Q1 and Q2 is the magnitude of the charges here and here. Distance is the distance between them. K is what we call Coulomb's constant. 8.93 times 10 to the 9. And the units are newtons meters squared per coulomb squared. The book uses 9. We're going to use 8.93 times 10 to the 9. Because if you consider that 9 is almost 7 million difference between 8.93 and 9 times 10 to the 9. Okay? No variables. All right. So let's look at an example here. Take a look at page 389. Find the force between charges of plus 10 microcoulombs minus 50 microcoulombs located 50 centimeters apart in air. Page 389. Okay? So, force is equal to K, 8.93 times 10 to the 9. What's the first charge on the positive guy?
I think their pages are different than ours.
389. 389. At the bottom, the example.
100.
Oh, what?
I'm looking at the top, I can find it.
What is it, Sammy?
100.
So 100 microcoulombs. You must change that to coulombs. So I times it by 10 to the negative 6. What's the charge on the second one?
-50.
Negative 50. Watch what happens here. I do not put the negative 50 in there. Do not put the negative 50 in there. Force is a vector quantity, so I need direction. So I'm going to explain why I don't put that negative in there in a second, and then I'll do it while I finish this off. And in meters, how far apart are they?
50. Oh, jeez.
0.5 square. Okay? So I want everybody to punch this into the calculator because we haven't done much work with exponent button. So use your exponent button, punch it into your calculator.
I don't have mine.
Do you want it in scientific?
It'll end up putting it in scientific for you.
1.786 times 10 to the 15.
What everybody else gets? I don't think so.
178.6.
That sounds more like it. Okay. 178.6. Do you see?
Right.
So 8.93 exponent 9.
Yeah.
Times 100 exponent negative 6.
Yeah.
Times 50 exponent negative 6.
I have positive 6, that's the problem. I think maybe.
Probably. I'll change things by that much. Anybody else not get that value? You're nowhere near that. Your exponent button is this EE button right here. You want to use it instead of trying to handle the exponent up. So try again. Use 8.93 exponent 9 times. That's all you need. That's what times 10 to the power. That means times 10 to the power up. Anybody else not get that? Casey, got it now?
Yeah, it was just I had positive 6, not negative 6.
Anybody else not get it? Okay, what's the direction of this? What's the direction of this? All I need from you, this is why I don't put the negative in, because you would get it as a negative. Don't put the negative in. Is it a force of attraction or a force of repulsion?
Attraction,
How come?
because it's opposite charges, so they're
Opposite charges. If you have a positive and negative, that means it is a force of attraction. And that's the direction you're going to put for right now. So you say it's a force of attraction, and that's the direction. All right? And we refer to this as Coulomb's law.
So if it's a negative and a negative, then we have to put the negative charge in. Both.
No, put them in. You know they're both negative, then you know it's going to be a repulsion because of the
So
same.
I should never put
I don't want you to put the negatives in. You'll understand why as we get going in this. But right now. Okay, so any questions about that? Everybody got that answer? May not get it? Okay. There's 2 questions on 390. There's 2 questions on 392. You can do the group A questions on 392.
March 10th. 1 to 16, it's 1 to 19.
And all of the group B questions. There's your assignment for today and tomorrow. Okay, are there any questions about this today? Shouldn't be, you haven't looked at it yet. You can continue, when we get to the end of this chapter, you'll go back again and you'll do more on the vocabulary. We'll do those at the end of the chapter. Okay? There's your assignment for today. Alright?
I'll actually like to that to make sure people are gone on Wednesday.
Okay, any other questions today? You shouldn't have to just yet. I want you to work on your own. Work on your own for right now. You have a break for that? We're using the break for the class time.
Can you grab my?
So what we did was, we wanted to